Hello everyone, I'm Dr. Feng, a postdoctoral fellow. Today I'm delighted to share my research titled Co-digestion of Polylactide and Kitchen Garbage in Different Anaerobic Methane Fermentation Systems. This study focuses on solving practical problems in kitchen waste treatment, while exploring the biodegradation of polylactide, a promising biodegradable plastic. Let's dive in. First, let's look at the two treatment process for kitchen garbage. On the bowl is the traditional process. Kitchen garbage, which is biodegradable, is mixed with non-biodegradable plastic containers. This requires separate collection, transportation, and separation steps before anaerobic digestion to produce biogas, creating high separation cost. On the below one is the new process. We use PLA-based plastic containers, which are biodegradable. Now kitchen garbage and PLA can be collected and transported together, directly entering AD for biogas production without separation. This not only simplifies the process, but also reduced cost significantly. To validate the feasibility of this new process, we set two core research objectives. First, to evaluate the biodegradable of PLA and thermophilic and hypothermophilic anaerobic digestion conditions. Second, to investigate PLA's biodegradation performance in different digestion systems, including single PLA digestion, no co-digestion with kitchen garbage, and combined temperature systems. To achieve those objectives, we designed a series of batch experiments labeled A to I, covering five key aspects: PLA degradation and thermophilic and hyperthermophilic conditions, co-digestion of PLA and kitchen garbage at 55 degrees, methane fermentation of pure PLA, and the promotion effects of hyperthermophilic treatment. All batch experiments were conducted at 55 or 80 degrees with substrates including pure PLA, pure kitchen garbage, and a mixture of both. For the batch experiments, we use sludge from a continuous reactor as the inoculum. The pretreatment process involved centrifuging the sludge at 3000 rpm for 10 minutes, washing it with hot water and collect the solid feces. This removes residual substrates and impurities to ensure experimental accuracy. The operation conditions were strictly controlled: working volume of 4.5 liters, hydraulic retention time of 55 days, organic loading rate of 6 grams COD per liter per day, and a substrate composition of kitchen garbage to PLA as 4 to 1 based on COD level. Let's introduce the substrate in detail. First, the artificial kitchen garbage. Its composition was based on a survey including cabbage, potato, banana peel, boiled rice, and small amounts of meat and fish, covering typical kitchen waste components. Its key properties are listed here, such as T as total solid as 191 gram per liter, Vs as 184 gram per liter, and total COD as 230 gram per liter. For PLA, we had two types provided by a company. They were cut into small pieces. PLA1 is a pure polylactide, while PLA2 contains 17% polylactide. Their total COD value are around 1.38 to 1.4 gram per gram plastics. For experiment A and experiment B, we added specific nutrients such as yeast extract and some other chemicals, following the formula by a previous study. We also tested the effect of ammonia addition with different concentration. The variables included reaction medium and PL types are summarized in the table. Each experiment had 4 replicates for ensure data reliability. The PLA transformation ratio was calculated by this formula, while SLCA is the lactic acid concentration and CPLA is the initial PLA concentration. The results showed a clear trend. The transformation ratio in experiment C and E is higher than that in experiment D and higher than that in experiment B and higher than that in experiment A. This indicated that hyperthermophilic condition and the presence of sludge significantly promote PLA degradation, while the thermophilic conditions alone are far less effective. We also analyzed the total ammonia concentration in each experiment. As shown in the table, ammonia concentration increased with the added chemicals. More importantly, the data confirms that adding ammonia can significantly promote PLA degradation. Higher ammonia concentration correlated with higher transformation ratio. This finding is crucial for optimizing the digestion system. Based on the above results, we promoted the PLA biodegradation process. First, under hyperthermophilic condition, PLA undergoes hydrolysis of ester bonds triggered by water. Then enzymes in the supernatant further break down PLA and larger microorganisms completed biodegradation, producing intermediate products like short-chain PLA molecules and lactide. Ammonia solution accelerates this process, converting PLA into lactic acid. Finally, under thermophilic condition, lactic acid is further fermented into methane. This process explains why hyperthermophilic condition and ammonia are beneficial. Next, we conducted experiment F and G to explore methane production. Experiment F focused on methane fermentation of pure PLA and thermophilic condition, while experiment G studied co-digestion for PLA and kitchen garbage. Both experiments used 1 liter of washed sludge, 10 grams COD of substrate, and ran for 6 days. We added chemicals for trace nutrients. Following a previous study, blank control without substrate were set for both experiments. The net methane conversion ratio of pure PLA was only 11.7%, calculated as this formula. We initially hypothesized this low ratio was due to acid accumulation inhibition, but further analysis showed no significant acid inhibition. Instead, the root cause was the low hydrolysis efficiency of PLA, confirming that PLA's slow hydrolysis is the rate-limiting step for methane production. In contrast, co-digestion of kitchen garbage and PLA significantly improved performance. The methane conversion ratio of PLA reached 39.9%, which is much higher than which is more than 3 times higher than pure PLA digestion. This proves that co-digestion with kitchen garbage promotes PLA's methane conversion, likely because kitchen garbage provides additional nutrients and buffers the system, enhancing microbial activity and accelerating PLA hydrolysis. We then test the promotion effects of hyperthermophilic treatment. The results shown in the graphs demonstrate that after 22 days of fermentation, most PLA was converted to methane when combined with hyperthermophilic pretreatment. This confirms that Hyperthermophilic conditions can effectively break down PLA, laying the foundation for high methane yields. To verify the efficiency of the combined hyperthermophilic and thermophilic system, we conduct a COD balance analysis for experiment H2 and H3. For experiment H2, 5.8 PLA was converted to 3.5 gram particle COD and 2.3 gram soluble COD and 2.69 grams methane and 2.01 grams methane in subsequent steps, resulting in a total methane conversion ratio of 81%. For experiment H3 with 2.3 gram soluble COD input, the methane conversion ratio reached 87%. Those high ratios confirms the combined system's excellent performance. To further validate the process practical applicability, we designed continuous experiment. The steps including multiple reactors with different temperature combination at 55 degree alone, 80 degree alone, and 80 degree followed by 55 degree. All reactors use PLA and kitchen garbage as substrate, allowing us to compare long-term operation stability and performance across systems. In the continuous experiment, we observed the relationship between ammonia concentration and particle COD dissolution. The graphs show that higher ammonia concentration promote PCOD dissolution, likely because ammonia induces the depolymerization of PLA and a natural polymer in kitchen garbage, converting particulate COD into soluble forms that are more accessible to microorganisms. Consistent with batch experiments, continuous experiment confirmed that PLA transformation ratio increased with ammonia concentration. When the ammonia concentration in reactor S1 and S2 rose from 1,000 microgram per liter to 3,000 microgram per liter, the PLA transformation ratio increased significantly, further validating ammonia's promotional role in continuous experiment. We also monitor the methane production rates alongside ammonia concentration. This confirms that the increase in methane production is directly driven by ammonia-enhanced PLA transformation. A comprehensive performance comparison shows that The hyperthermophilic and thermophilic combined system outperforms the single thermophilic system in all key indicators: methane conversion ratio, Vs removal ratio, COD removal ratio, and PRA transformation ratio. This provides that combining hyperthermophilic pretreatment with thermophilic digestion is the optimal configuration for kitchen garbage and PLA co-digestion. Based on batch and continuous experiment, we draw three main conclusions. First, hyperthermophilic treatment significantly promote PLA biodegradation compared to thermophilic one. Second, adding ammonia accelerates PLA's conversion to lactic acid and subsequent methane production. Third, the hyperthermophilic and thermophilic combined system achieves better overall performance than single thermophilic systems, providing a feasible technical route for treating kitchen garbage and PLA plastic. That concludes my presentation. I'd like to thank my research team, funding supporters, and everyone here for your attention. If you have any question or suggestion, please feel free to ask. Thank you.